Evolution colloquium series. Enrique Noriega, PhD candidate, is going to tell us about focus reading.
Thank you very much. So, I'm Enrique Noriega, and today I'm going to talk about focus readings. Focus reading is my dissertation project, and it's a work that we've been doing myself along with Marco Valenzuela, Clayton Morrison, and Mihai Suganu. And the motivation of this work, part of the motivation is the observation by Don Swanson, where he states that knowledge exists out there as little pieces of information that are disconnected among them. Hence, they're undiscovered because they haven't been put together and analyzed before. And one of the reasons of this is that scientific productivity has been increasing substantially during the last years. This plot here is the amount of biomedical publications, and you can see how it's been growing during the last couple of years at an exponential pace. So, because of this, no person can keep up with this. It's impossible that a human being can read all this knowledge and analyze it in a meaningful way. But we can use machines that we have today. And this has driven the field of information extraction to make a lot of advances during the last 30 years. Information extraction, what it does is that it takes unstructured text and it gives you back bits and pieces of structured information out of that human written text. But it has some problems. We still need some help. We cannot just apply information extraction over a huge corpus of documents. What are these challenges? It's mainly that it's expensive. And it's not all, and I mean it in a way of computationally expensive. Not everybody works in a place in which they can afford all the computational equipment from information extraction at a huge scale. So we can do it up to a certain degree because we have a lot of computers in laboratories and we have high performance computing facilities. But if you're an individual researcher or if you work in a company in which your main focus is not doing information extraction, but you want to use it to aid some of your bottom line projects or products, you cannot do it that easily. It's also not a solved problem. By this I mean that since it's in the end a computer system, it's going to have bugs, and that those bugs needs to be fixed, or some expert might come up with a new grammar rule that he writes, or if it's a machine learning based information extraction system, you might come up with a new model, and this means that you need to retrain it. And all of this also means that you need to rerun the whole system across the already processed data sets. And this, as we saw before, is expensive. And last but not least, not all the information is available for free. As an example, take PubMed. PubMed is a very popular repository of medical research publications. It's huge, but only about 20% of it is within the open access subset of PubMed. All the other documents are behind paywall. How can we overcome these challenges? So, most obviously, we do not need to read everything. We are only concerned about the subset of documents that contain information that is relevant to our questions, hypotheses, and queries. But how could we know which documents are those? So these are the important documents, and to find out which are those, here's where focus reading comes into play. Focus reading is a way to put together information retrieval and information extraction into a guided iterative search process. And what do I mean by this? What questions can we answer by using focus reading? Those are questions of this form. Given context C, how does X affect Y? So this is kind of abstract, but here are some particular examples of these kind of questions. In the biomedical domain, for cancer, how does Picre kappa affect KTF? Or in the news, how did Obama reform healthcare during 2012 to 2016? Or in the security domain, how do drug cartels disrupt the Mexican government? All these questions have in common that we have two particular entities that are of our interest, and we want to know how one affects the other, but we also have one context, and these are color-coded in the slides here. So the context is a blinder, and this blinder allows to restrict our search to a subset of documents that we want to discover. So this is going to help. To answer these questions, we need, at a high level, two stages. We need information extraction to extract those individual structured pieces of information, but they are almost always within the same sentence because they rely on grammatical structures, and could also be within the same document because you could use some discourse phenomenon like reference, but they never, you cannot do information extraction this way across multiple documents. And this is why we also need information aggregation. Information aggregation allows us to combine those individual pieces of information into longer explanatory paths. So the paths are just those pieces of information connected together in the same fashion as Don Swanson stated that you could put them together and discover the previously undiscovered public knowledge. So this can potentially happen across multiple documents. One particular example of both are how A activates B. This could be in biology. An activation is a biochemical construct or concept. And for information aggregation, a protein signaling pathway. So a protein signaling pathway could be a chain of those activations that we saw above. So how can we visualize what's focus reading? So you could argue that focus reading is a fancy way to say a heuristic bidirectional search within a certain context, and context meaning that you're searching across documents. So take, for example, this question or this query. How does protein 1 affect protein 2? We can represent the elements of our search as elements of a graph. So take protein 1 and protein 2. We can put them together into a search graph, which is initially empty besides those entities. But then we can use those to do an information retrieval query. This is going to give us some documents that contain those proteins, and we can then apply information extraction on them. After we do that, we could add them to the search graph, and we can see how it starts growing. It's growing wider because we added new elements, new nodes, and new edges. In this particular example, the nodes represent biochemical entities, and the edges represent biochemical reactions. So take, for example, protein 1 interacts with whatever entity is this other node or all these other nodes. Likewise with protein 2. And what happened here is that we grew that search graph. We expanded the fringe of our search. So now we have more information, but we still do not have the answer of how does protein 1 affect protein 2. So we can apply this process iteratively, multiple times. And we will see that the graph is going to grow and keep expanding the fringe of our search until eventually we can find a directed path. Or we couldn't. So that would be the failure of the algorithm, but the success case is whenever we find a path. So this path becomes a hypothesis. This hypothesis gets passed to a human researcher or whoever is the user of our system to validate it and to use it. This is another representation graphical representation of the focus reading algorithm. We said that we can do information retrieval and information extraction, but we can do it multiple ways. So we're still keeping it higher level, and we will start digging into more concrete ways to apply these steps to build up the whole algorithm at the end. So again, we start with our entities of interest. In the first iteration, we grew the graph, and in this particular example, it's round, such that we see that the components. So a component in this context is basically the topology that gets formed in which the entities of interest are in the middle or are contained in that connected subset of the graph. And they become wider because we read a lot and we extracted a lot of information. Of course, when we read more, we're spending more resources in money if we had to pay for the articles that we read, or in computing power if it's thousands and thousands of documents that we need to process. We can repeat this multiple times, and we'll see that we gain more information. So this It's possibly more productive, but it's not the most efficient way to do it. But we need to do it because we still do not know what we want to look for. So we're getting more options to eventually focus our search. So whenever we do this, we call it the exploration strategy. The exploration strategy is likely to find a connection, but as I was telling you, at a higher cost, because we basically do much more of the work that we need. But at some point, hopefully, we'll have enough information such that we can focus on particular elements of the graph that we estimate will lead us to find the missing pieces of information that are going to bridge the gap between both components. So in that case, we will issue a query that will give us few results, but hopefully more meaningful results. If we repeat this in this example multiple times, we say that we're following an exploitation strategy. So what was the difference here, at least graphically? And that in the first two steps, we grew wider our components, so we added more information. And in the later two steps, we started focusing on particular elements that brought in fewer elements to the graph, but were specifically designated to find the path that connects the green node with the orange node. So now we made a statement about how to do information retrieval and information extraction and information aggregation. But when do you know when to do exploration and exploitation? And that's the heart of the focus ring algorithm. So this is the algorithm, or at least some sort of very high-level pseudocode. It's mainly 6 steps. In the first step, we choose the entities for an information retrieval query. In the first time when we start, we only have A and B, which are the entities of interest, and that's it. So there's not real choice there. But after the first iteration, we'll have more. So which of those to pick? We want to know how initially how A interacts with B, but then we will introduce C, D, and E. So what if you think that D and E are more relevant here to close the gap? We could choose it. But we will apply one of the coarse-grained strategies, exploration or exploitation. And in this case, the particular implementation for this, at least this stage of this work, exploration in step 1 means picking the entities that are the most connected and belong to the same component of the entities of interest. That means the centers of the star, the ones that are related to the largest amounts of entities that we extracted. Or exploitation could be pick the ones that were the most recently added. One of the most recently added entities, because intuitively that could lead us to something that we didn't know, and we think we can dig down or double dip into those entities. Then we need to build an information retrieval query itself. There are many ways to do this, but since it's a binary query in which we care about A and B, we can apply the exploration strategy by doing A or B, and the result of this is going to be a set of documents that contain either A or B or both. So it could be that they contain information that will help us to our search, but maybe not. Maybe it will, but indirectly, because it could be A and something else that is not yet in the graph. Or we can do exploitation, where we change to a more constrained version of the query in which we require that both elements are in there. So this constraint, by enforcing it, we will possibly get an empty result if our choices of entities A and B was not helpful at all, or we could be lucky and get the paper that we need to bridge the gap. But at least we will know for sure that the documents that we retrieve by issuing A and B are going to contain both in the same document. The rest of the steps in the focus ring algorithm are deterministic and well-defined. So there's no knob or lever that we can choose there or change. So we fetch the documents, we extract the information using information extraction, we add the findings to the search graph, and we evaluate to see if we found the path, or otherwise continue until we finish, or until we decide that we have spent our wheels enough time, but that we quit. So, the way to choose when to do exploration or exploitation is where this becomes interesting. Here's where reinforcement learning comes into play. So reinforcement learning is a way that lets an agent, which in this case is a computer system, learns to take an action given out of a set of possible actions and execute it. The result of this, executing this action, is a reward. So reward is a measure of how good was this action. It could be positive, it could be negative, or it could be neutral. And by trial and error, this agent is going to repeat the actions and change its state. So one good example of reinforcement learning could be me. I could be an agent and say that there's a table with some pastry up there. So I could just start walking randomly across the room, and my actions could be take a step on any direction I could, or try to grab something, or try to bite something. So I could just start walking and try to grab something, but obviously if I'm not in front of the table with pastry, I will not grab anything. So if I try to grab something and there's nothing there, I will get a negative signal because that was useless. So eventually, theoretically I could repeat this an infinite number of times, I could end up in front of the table that contains the pastry. So I could grab that pastry and then I could try to bite it. Since I like pastry, I will get a positive reward out of that. So the next time I try it, I would already know that that was good. So I will be biased towards taking that action before, until I find policy. The policy is just a set of rules that tells me which action I need to take that will lead me towards the pastry directly and eat as many as I can. So how can we translate this goofy example into focus reading? Well, we need a state. So the state in this case is the search graph and the search process. And it contains information about the entities that we have found already and which step we have taken before. So for example, if we choose C and D, how many times have we chosen C before? How many times have we chosen D before? This could intuitively lead us to believe that if we are choosing an entity multiple times, it's informative. Or how connected are those entities to the search graph? That's another proxy to see how relevant is that entity at least in that biochemical context. The actions that we have are basically the strategies that we were explaining before. So these strategies, exploration and exploitation, need to be concretely defined in all the points in which they can be applied. So if you remember the pseudocode, there were two steps, steps 1 and 2, which you can apply both strategies. In this case, it would be just the Cartesian product. So you could follow exploration by choosing the entities that were the most connected, but then you could use an exploitation query that issues a disjunctive query. So you could do any combinations of both. And then you take that action. So you execute the rest of the steps of the focus reading algorithm, and you will observe the state after you finish. So after observing that state, you will get a reward. So the reward is just a measure of, after taking an action, given the state in which you are, and in this case the state is the graph, the search graph, and how many times I have repeated the algorithm, I will either find a path or not. So if we found the path, we are done. So that's good, and we can present that to the researcher or to the user. So the result of this is a positive reward. But maybe we did this a thousand times and we couldn't find it. Maybe it doesn't exist and we're wasting our time. So if we didn't, we return a negative reward. But also we want to do it as quickly as possible because each step that we take means that we're reading more documents. So why are we spending resources in stuff that is irrelevant for us? And that's when we introduce a small labor reward that is a small penalty that biases the process to be as fast as possible. So it tries to find a policy. And by policy, again, I mean a decision rule to choose the strategies on each step that maximizes the chances of finding a path as quickly as possible. Not just following around for a while until I decide that it's time to get to work and find a path. So for this solid theoretical framework, and we eventually coded this into an actual system. For this experiment, we need a data set. And the data set is composed in these experiments of two components. First of all, it's a corpus of documents that we're going to use to find information. And we also need a baseline of queries or questions. So for the queries, we use the DICE model. The DICE model is a model of biochemical interactions of human pancreatic cancer that was built by real biologists. So we know that whatever is there exists. And our corpora is the open access subset of PubMed. So we took that subset of PubMed and built an information retrieval index with Lucene. So you could think of this as a mini Google in which you can issue queries and we'll search those documents in your computer. And then we use those interactions as seed queries. So we will try to find how these two entities interact within that corpus of documents. So presumably, since we know that it exists, it could be somewhere among the 1.5 million documents that we were able to index here. So we took this corpus and ran REACH. So REACH is an information extraction system that was built together here in the university by the Computational Language Understanding Lab. And the result of doing REACH is that we will get these tuples here, which represent these semantically the same as these connections in the DICE graph. But the data source is different. This was built by someone, and the extracted interactions are the result of reading the subset, the open access subset of PubMed. And then we can put together those interactions and build what we call the REACH graph. So it's basically the network that we cast by taking those extracted interactions. And the end goal here is to see how well can we fit the hand-coded pathway to the REACH graph. So ideally, all of the information on the left should be on the right as well. But we will see how much of that we can find. So this becomes our data set. But we also need a baseline. So what's a baseline? We need something to compare our learning algorithm to. And for that, we can hard code a policy of focus reading. What do I mean by this? Is just basically let the agent or the computer always choose the same actions deterministically. In this case, the baseline follows a back-off strategy. And again, what do I mean by this? Is that it will always issue exploitation because that's more conservative in resources. So it will try to spend as few energy and computation resources as possible. But if it didn't find enough information to expand that search graph, it will back up to an exploration strategy in which it will relax its constraints and will get more documents to read. You could argue that this by itself is a full-fledged system of focus reading. But the idea here is to see if there's any other combination of actions that yields a better result than this, and how can we find it. So, out of the DICE graph, we were able to recover 289 paths by reading 70,000 documents. So, the way we found this was basically brute forcing the search over the whole REACH graph. But obviously you don't want to do that in the real life scenario because that's exactly what we're trying by using focus reading. We only need that to see how well we do related to our best possible attainable performance. If we apply the baseline, we were able to recover 65% of those paths, that's 199, by reading about 35% of the papers. Then we use reinforcement learning, and we learned the policy to select those actions. And the result is that we were able to find 3% more paths by reading 25% fewer papers than baseline, which is a good improvement in performance. So all of this is great. Now I want to take a look into what do I mean by learning? So how does that trial and error looks? So in this plot, each bar represents a training episode. So training episode is give me a query and I will choose the actions to see if I find the path or not. At the beginning, the agent starts with no prior knowledge, and it by design chooses the exploration strategy. So by repeating multiple times that current policy that it knows, it will always follows what it can do without information until it learns enough to start making a trade-off. So the proportion of colors on each bar represents the proportion of strategies that were followed during that training episode. We can see that at some point during training, it started making that trade-off. And eventually that trade-off started happening more often than before. But we can see that it doesn't monotonically increases or decreases, but it starts adjusting, because always that agent is going to start making, or is going to be exploring to see if it can take newer actions that it hasn't taken before, to see if they improve or over what it already knows. Eventually it settles down, and that's the result of the last bar. So what we found out of this work is that there exists an efficient policy that improves over an intuitive baseline. And this framework uses domain-independent information to find that policy. That means that we're not using any biology whatsoever, besides the name of the proteins that we look for information retrieval, to guide our process and find the policy. It's adaptable because we can add more information to the state. We could use more information of that search graph to take the decision of which strategy to follow at each point. And there are a lot of extensions that we're currently working on. For example, expanding the dataset to, instead of just using the DICE information to derive the seed queries, we're exploring whether we can use a denser or larger set of biological interaction models. We are also interested in branching out of biology into question answering, and we're also experimenting with adding finer grained actions that instead of using exploration or exploitation is explore a lot, or explore just a little bit, or exploit very focused, or just so instead of having a discrete set of actions, have a wide range, still discrete, but a whole spectrum of versions of those actions. We're currently also working on incorporating expert knowledge to the learning process. So, as you may recall, I stated that with reinforcement learning, you learn by trial and error. So you know really what you should do until you observe a reward that tells you whether the action you took was good or not. But you could observe someone do that search before. Say, let's go back to that goofy example. If any of you stand up and walk towards the pastry tray and grab one, I could observe that and say, oh, he did that, so probably I should do it too, and that will aid the learning process. So in this case, the paths that already exist, that we brute force before, could serve as another as an expert that we could try to imitate. So that's known as imitation learning. We can also use reward shaping. So reward shaping is playing with that definition of reward signal to see if we can bias the agent towards certain actions that we believe that are more helpful, such that it will increase the speed of learning. Say, for example, if somebody took some of those pastries and put them on the ground as a trail of breadcrumbs, I could follow it because I like pastry, and I could see, oh, there's a small pastry lying on the ground. I could take it and start seeing all of these until they take me to the tray. That could be some sort of analogy with reward shaping. We're also interested in discovering if there's a better reward structure. You may recall that I said that we have a small positive reward if we succeed, exploitative reward if we didn't, but how are we sure that this is the optimal reward structure? We're not, we do not know. So that's our intuition. But we can do inverse reinforcement learning, in which instead of trying to learn the policy, we're using the expert knowledge to try to learn what's that reward structure. So possibly we could learn that reward structure and then apply it to regular reinforcement learning to see if we find a better policy than what we have right now. And also there are some other approaches besides reinforcement learning. They're called evolutionary strategies, also known as genetic algorithms, in which you randomly change the policy, but keep track of which of those give you the best return, and then mix them together, hoping that they will give a new policy that is better. So you start creating some variations until you eventually settle down into a policy that gives the best overall return. The difference with reinforcement learning is that you're not evaluating how well the actions you took fared to update the policy. Instead, you randomly shuffle the rules in the policy and just keep those that perform better than the ones you had before, and then try to mix them. So that was it. Any questions? Thanks.
This is just a question of clarification.
Mm-hmm.
I guess I wasn't completely clear on the respect in which the algorithm is learning sort of general policies for finding connections to solve a certain query, and the degree to which it's learning in a sort of a more specialized way about a particular domain. So for example, if I start out, I ask about protein 1, protein 2, and then I think, well, I'm also interested in protein 3, so it seems like some of this could help at both levels, but I just wasn't getting a clear picture of that.
Right. So I could say that it's half and half, because the features that we used do not depend on biology. So we could presumably say that it extends, and we're interested in testing this. But as with any other learning process, it all depends on the data that you have. You could use the exact same features to adjust your decisions, but the instantiation of those features could be way different, or the search graphs could look very different if you go to another domain. So if you already learn a policy that works in biology, you try to take that policy and apply it into, I don't know, movies or something like that, I'm not sure, but I can bet that it won't work. So you will need something, a training data set that comes from the same source, meaning movie questions or movie reviews, to train it and find that policy using the same representation that we used before.
So this is a very, very good question, and I think it's one we need to work on having a clear response to. In fact, this is something that should be appearing in dissertation papers.
Mm-hmm.
So, I think you had at least the answer that I also believe in to this question is in what you said, but to try to draw this out. Your question is about the relationship between strategies and then the state of search representation that we're using. So the state of search, the representation of the state of the search is this growing knowledge graph. That knowledge graph is domain independent in the sense that we don't care what are in the nodes. All we're doing is we're capturing basically the topological linkages between them. So the strategy that is learned, this is also something we empirically should actually study a little bit. I believe that the strategy that is learned, in one sense, it is domain general because we don't care about the entities or their links, we just care about their topology fundamentally. But I do think that different information domains might have different kinds of topological structures. And because of that,